Great. Conservation of momentum, specifically collisions. So we're going to talk about the types of collisions. I do list one more than textbooks tend to. You'll understand why after we get to it. So, broadly, they fall into a number of categories. There are elastic collisions. They're relatively less common. They are collisions in which the kinetic energy is also conserved. So, in other words, it's a case where the change in kinetic energy, delta Ke, between the initial and final case is equal to 0. This actually gives us a second condition that we can use to solve problems, and it gives us another equation we can use to solve problems. The thing is, they're relatively uncommon in reality because you need to have a conservative force acting and no non-conservative forces can act. And for most real systems, like two carts colliding with each other, a car colliding with another car, a bowling ball colliding with a wall, just about anything like that, you're going to have some losses due to resistive forces somewhere. There are cases where it should be completely conserved, and those would be cases where you're interacting with just the gravitational force, like two planets interacting, colliding, not literally touching each other, but gravitationally interacting with each other. Or two particles like two electrons or two protons colliding with each other on a subatomic scale. There are a number of collisions we can treat as approximately elastic. For instance, the collision between a steel plate and a steel ball, or between two steel balls, would treat that as at least approximately elastic, and it works fairly well. Okay, the other broad type would be inelastic collisions. Simply, an inelastic collision is a collision in which kinetic energy is not conserved, which would be every other type of collision you can think of other than the elastic collisions. There are two special cases here. Perfectly inelastic, which you hear talked about in textbooks. In a perfectly inelastic collisions, the objects stick together after the collision. This makes things a whole lot easier to figure out. It removes a whole parameter from everything we need to consider because they stick together and move off together after colliding, and that makes things a lot simpler. The other one that textbooks don't talk about, and is kind of just me making my own thing up, is that there are explosions. And in this case, the objects start together but split apart. This would include literal explosions, like you have a bomb in its casing and then it blows up and the pieces go flying everywhere. Or, somewhat simpler to think about, would be like a bow and arrow where you let go of the bow and it fires the arrow. It's like an explosion. These are both interesting because the kinetic energy is not conserved in very particular ways. So in the case of a perfectly inelastic collision, the change in kinetic energy, delta Ke, oopsies, is less than 0. Less than 0? Yeah, you lose kinetic energy. Your final kinetic energy is less than you started with. The interesting thing about explosions is they're the opposite. The change in kinetic energy is actually greater than 0. And I'll also add a note that the change in kinetic energy just for general elastic collisions, redo the E entirely, is simply not equal to 0. Okay. Not all inelastic collisions are perfectly inelastic. Not all inelastic collisions are explosions. These are relatively rarer cases. There are a huge number of inelastic collisions and types of inelastic collisions. Two cars hitting each other at an intersection is an inelastic collision. But it's not usually perfectly inelastic, they don't usually stick together, and it's certainly not an explosion. Okay. All right, in any of these collisions, in all collisions, the momentum should be conserved. So for everything mentioned above, the change in the momentum delta p should be equal to 0. That is functionally guaranteed by Newton's third law, which is functionally guaranteed by space being mirror image symmetric. You can swap things from one side to the other and it doesn't change how the physics works. So this should always be the case. If it's not the case, then that's usually because you have a resistive force that is acting on your system all the time that you're failing to account for, and is causing very small losses of momentum at any given moment. Essentially, it becomes an impulse momentum problem, where you have this small impulse caused by a resistive force which causes a change in momentum to not quite be 0. Okay, so that's types of collisions. We'll get into more details with those with examples when we get the chance. For now, this is what you need to know, the bullet point version, and we'll stop there.